thank you very much for the honor of being here. It's fabulous to come all the way to Singapore to deliver this talk. I have 10 minutes, I'll be going fast, and I really want to go over a personal story. And the story is that of what it's like to innovate materials-intensive technologies for energy application, in this case, going from the lab all the way to a finished product. And the story is very different for a materials technology than it might be for another kind of innovation. When most people see the word innovation, they think of something like this. We have some computer programmers, some money, some Red Bull. They work for less than a year, and they take in less than $1 million, and they make much more at the end. They're able to create a game-changing computer app or website that will, in principle, move the bar for society. It's very inexpensive, it's very fast. However, if you want to innovate on a materials-intensive technology, you need to think more along the lines of this. This is the Tesla Gigafactory that's being built right now in Nevada. It, in theory, will be able to produce 35 gigawatt hours of energy storage per year. It will take 4 or 5 years to build, and it's taken 30 years of lithium-ion battery research to get to the point where we are, as a society, prepared to build a factory this large. And I want to pause for a moment just to sort of a plea to the research organization, and that is, if you're doing research that is materials intensive, that is for energy technologies, keep this scale in mind. This plant will process between 14 and 18,000 kilograms of active functional material per hour, every hour, all the time. And that's a tremendous amount of scale and a tremendous amount of mechanism that is required to get to something that can move the bar at the global level. Our energy question is a global one. And so understanding that and putting in the context of what you're doing in the lab to this huge scale might lead you to some conclusions about how to do things differently or sort of in a more scaled fashion more quickly. And so this is the question that I took upon myself in 2008. And specifically, there was a hole in the technology, energy storage-wise, and it was for low-cost, stationary, long-duration storage. So this is for applications where you have about 4 hours to charge and 4 hours to discharge or longer. And the idea was at the time solar panels were becoming less expensive, and there would be a desire to take all diesel generation, all other generation away and just have a solar panel that could supply energy all the time. You would need a battery to do that at night. And so the concept was to develop some very low-cost solution that would go along with the solar panels. And to start with, though, to be really clear, you have to look at the money, because electrons and dollars, at the end of the day, are fungible. And so you can't have the impact that you want if you can't sell for the right price. And so this leads you to what must be the key materials metric for any device that's energy related. And that is dollars per watt hour processed, or dollars per watt, depending on what the technology is. In this case, it's energy storage, so it's watt hours, we store energy. And this is both watt hours at a capital cost on day one, what you pay for the device, and also what you pay over the lifetime of the system for watt hours that have been stored inside the device. This number has to be compelling. If it's not, you will never get to the scale that you need. So, what's low cost? Salt water, it's essentially free. Sodium is essentially free. Manganese oxide is very inexpensive. Carbon's very inexpensive. And so these were a handful of the materials that I screened initially to figure out if this was possible. At the time, no one was looking at aqueous electrolyte, sodium-ion intercalation battery systems. The idea was to do something like a lithium-ion battery, but with sodium and in water. And the first device turned out, after a bit of plugging around and standing on the shoulder of many great researchers who've done work in this sort of aligned fields over the past couple decades, was this, a sodium manganate cathode material. This is really made by mixing very low-cost manganese oxide and sodium bicarbonate and heating it up. It changes phase, it becomes this functional material. An activated carbon that's low cost on the anode side, and when you charge it, all the sodium goes to the anode, the negative side, and when you discharge it, it goes back to the cathode. Fairly simple. And it turns out that it worked well enough to get some good publications, and it was stable. This is the most important thing. This has to last over thousands of cycles. And the data that we showed early on showed this was possible, that we'd have no loss in function over many thousands of cycles. It's a critical attribute of any energy storage technology, and it was made from cheap materials. So at this time, it seemed like we might have something. So from this invention phase was sort of, this initial invention phase was kind of ending. It was time to do some more innovation. and then you realize that everything is new. This is not a traditional battery chemistry. It doesn't have the same kind of electrodes. It doesn't have the same kind of electrode structure. The packaging needs to be different. The way you think about integrating it to a system needs to be different. The way you might treat it electronically could be different. So that's a real challenge, and you have to take pause and press a reset button and go into this fresh, not using existing paradigms for batteries or energy storage. A key thing we decided to do early on was to only use repurposed or existing manufacturing technology. If you have to also invent a new manufacturing route, you're doubly behind in what you're trying to do. And so trying to only invent new materials based on things that could be scaled using existing technologies was key for us. We failed fast, and it seems kind of funny that you would claim success by failing, but in fact it's exactly the case. The faster you can recognize when something is not working, the better off you are to stop it and move on to something that will work. And whenever you find something that's a failure, that's actually great because you know what to not do. And you can then change your focus, move different place, and make the right choices at the end of the day. And we also made the decision to start to scale our pilot line and even our production line before we had a final design in place. This is a really risky thing to do, but if we hadn't done it, we'd be 5 or 6 years behind where we are right now. It was a logical step given the time domain that we had. So after a couple of years and some more money we spent, we ended up with this. And it doesn't look like that exciting of a picture. This is one of the electrodes of the battery system that we now manufacture. But this is the key building block. All the special sauce is in this little 6 centimeter by 6 centimeter by 1 micron thick pellet. Inside of this is a tremendous amount of material science. It has to do with how the materials are produced, how they're bound together, what kinds of conductive additives are there, what kind of porosity it has, how consistent the grains and the particles are inside of it. It's been a very amazing process to understand, you know, not only can you make one of these, but can I make 1 million of them a day? And can I put them into batteries that really have an impact in the real world? And part of this process also was developing a way to do this. And on your right there, you see the pellets coming off a rotary dial press. This is a repurposed technology. We can make hundreds of them a minute. And on the right is the very first sort of pilot line that we had. It was all people. We were making batteries by hand. 10 people standing around this dial table. Everyone puts in a cathode or an anode or a current collector or a separator, and you build up the layers of the battery, and then you test it. And sort of our first pre-prototype or production pre-prototype looked like this. We call this the Battery Zero. It has a polypropylene injection molded case. This proved that we could seal it and use this kind of material. And inside are just stacked up sets of the electrodes that I just showed you. And it was lovely at the time. It allowed us to answer some of our early funding from the Department of Energy. But the question, was it good enough to be a product? No way. It wasn't even close. It had all kinds of problems. But it was good enough to keep going. And this is another important lesson about innovation with materials, is that you are not going to get to the final solution initially. You're going to get to different steps along the way. You need to recognize what those steps have to look like, and you have to make sure that you hit them. And you have to make sure that the people who are interested in continuing to fund your work accept those, right? So an early intermediate milestone for us was creating this kind of device that showed the promise of manufacturability and function. But we went back to the drawing board. We changed our material system wholly. We changed our manufacturing approach to a large extent. But at the same time, we were growing our pilot line and growing even the production line. And so there was this tension. We no longer could be super agile as a startup. We were still using imperfect data to make decisions. We were going very fast. But now that we were setting up larger pieces of equipment and committing a large amount of capital, we also had to go slow. And there's this idea of going slow to go fast so that you make the right decisions the first time. And you've got all this stuff that's sort of conflated. And there's a real tension. And at the end of the day, you figure out ways to resolve the tension. And one of the key decisions that we made is that we're only going to commit to flexible manufacturing technologies. What does this mean? Not only is it repurposed and existent for other fields, but it also, we can buy one piece of equipment and we can imagine many uses for it, as opposed to committing to a very expensive, singular, monolithic thing that only does one kind of manufacturing. We made that decision exactly one time, and unfortunately it's sitting on the floor in our factory not being used right now. Since then, we've been very careful to invoke broadly usable equipment and different processes that we know we can use in different ways, because nothing is going to be constant, we're realizing, in the first 5 or 10 years of this technology. So a couple more years and about $40 million later, we have now a fully productized solution. on the left is a cutaway of the inside of this battery. You can still see the fundamental building blocks, those electrodes, those little square pellets. They stack up in anode-cathode pairs, and there's 4 cavities, each of which are connected in series. So each of these batteries is an 8-volt thing. And then we put 8 of them together to build up to about 55 volts. And this unit has about 3.5 kilowatt hours when it's fully charged. And we can distribute this around the world to paying customers who will put them in a variety of places. But just as important, we were able to repurpose, and I'm not kidding, candy manufacturing technology. This is the same stuff that puts chocolates in boxes for Valentine's Day and so forth, except now it's placing our pellets in the right locations. And you can see in the upper right there, there's an optical interferometry system locating the pellets and putting them in a tray system. In the lower right, they're picked up and placed inside the battery. This is in a factory just outside of Pittsburgh. We're lucky to have employed over almost 200 people over the years, and we are in now full-scale manufacturing. And it's been fantastic to grow out of the university, out of CMU, and put this in a local region. This is a picture of something I'm really excited about. We just brought online our biggest installation to date. It's 1 megawatt hour. It's on Hawaii, and it's tied with a big solar farm, and it allows the microgrid users of this system to be completely diesel fuel free in perpetuity. There's enough storage in the batteries for up to 3 days of use without having to recharge. And furthermore, I'll end with this. We have over 100 installations globally now, over 15 megawatt hours installed, and this is all less than 7 years after the first proof of concept in the lab. And what I really want to communicate is that this can be done. You can go faster than 30 years, and you can do something that may have an impact without spending $5 million on a plant. But you got to make the right decisions. You have to learn how to fail fast, and you have to learn how to scale your stuff, your materials processes, to be commensurate with existing manufacturing technologies. Thank you.